Welcome, everyone. Happy webinar day. Today's topic is, as you see on the screen, build it tight, ventilate right, and ventilation with heat recovery. We're really thankful to 475 for being a part of putting this together for us. Passive House, California. Thank you all for being here. We are part of the Passive House Network in New York, and of course the Passive House Institute and Passive House International Passive House (IFA). So we're here, and first of all, I want to thank High Performance Building Supply. They've been one of our sponsors for many years, which we much appreciate. And they've done many webinars over those years. Today's webinar, which you can see dimmed there, that's there. I put it there. So I want to thank you to 475. Thank you to our silver sponsors, Small Planet Supply, Minutair, and Earthbound Homes. And then to our supporting sponsors, as you see there, 475 was the first one, then Rockwell, Fergus Garber Architects, Ream, Hayward Lumber, the Heinrich team, that's a realtor, Pete Moffett, Steve Eltron, who's another water heating and things, CPHBA, The Good Space, High Performance Builders, Pasoko, Intelligent Membranes, and we have a new sponsor that just came on board. A supporting sponsor is Todd Jersey Architecture. He is taking the class. Todd is becoming a certified PhDC, and decided to jump to become a sponsor as well. So that's who we have as sponsors going well. So instead of the call to action, which will be coming up later, I will stop my share and we can get Gabrielle can sign or put her stuff up, and we're ready to go.
So today the presentation is build it tight and ventilate it right. I'm going to be talking about a little bit about what goes into a high performance building, and which leads us to require mechanical ventilation with heat recovery. So a little bit about me. My background, I grew up actually around a family of builders. My grandfather was a cabinet maker from Austria, and there's his shop in the middle photo there. My parents built the first house I grew up in, so grew up really loving buildings, drawing blueprints. Everyone thought I was going to be an architect, and then I loved beautiful buildings, but I wasn't sure, I didn't understand fully how that would help others, and that was important to me, giving back. So undergrad, I actually ended up being pre-med and was working in healthcare. I worked in cardiology, pulmonology, worked in the emergency room. So I worked in healthcare for about 4 years. And what I kept seeing was a lot of repeat, people coming in with very poor health, very poor diets, environmental issues leading to their illnesses. And I also ended up moving to Colorado and learned a lot about green building and ways that buildings could actually impact our health, which led me to go back to grad school, kind of because I still had that passion about buildings. I got my master's in sustainable urban infrastructure. After that, I started working in commercial buildings, large chiller and boiler plants. And this bottom right-hand photo is a building automation system. So trending BAS data, looking for opportunities for energy efficiency there. From there, I joined 475, a company that I had known about through my graduate school program. Thought of it as a great company. One of the things that I like about us and them at the time was that not only are we interested in high performance buildings that use low energy, but also really care about the materials that are used to do that. So we are very much about looking at the composition of the materials, working with more natural insulations, along with our airtightness materials. Our airtight materials are zero VOCs, so that was very important to me. So at first, at 475, I was working with the envelope materials before our centralized brink ERV and HRV solution was brought here. The Brink ERV systems have been around in Europe, the company over 40 years, so tried and true and tested. They're used the go-to for high performance homes and homes for proper ventilation all throughout Europe. At 475, we believe airtightness is key. So that includes, doing blower door tests to make sure that your mechanicals are sized as you design them, because without testing that, you don't know for sure that you don't have that leakage. And we'll get into details, but we know that airtightness is key for energy performance. So sounds like the audience probably knows 475 a bit, but we are an e-commerce website, so there's a lot of information on our website. You can, we have CAD files that you can download on there. There's ebooks, there's blog posts, all sorts of information on our website about the materials and products. So here's a little bit. So there's the CAD details there for various construction types. We have our air sealing and vapor control layers. Again, these couple really well with natural fibrous insulations. So we try to stay away from foam insulations. And so when you do use these, we want an airtight material on the inside and a wind-tight material on the outside while thinking about vapor diffusion. Continuous insulation product here, and high-performance skylights is something we also work on. Today we'll be focusing on heat recovery and energy recovery ventilation. We have a decentralized solution as well as a centralized solution, and just a summary slide there. But let's get into the AIA and PHI presentation today. That there, but as we saw in the course description, we're going to be talking about the relationship between air tightness and a building's comfort, energy efficiency, risk of condensation, rot, and mold, and the benefits of mechanical continuous balanced ventilation with heat recovery for buildings and occupants. We'll describe the differences between various systems and then talk about the components and how to create a nicely run system. So here, I'll also show this at the end for those who don't scan it. Maybe we can put it, if someone wants to scan it, and then you can put in the chat maybe the link. That's just to get the AAA credit for today, as well as a little survey. Just would love to hear what you think about how technical the presentation is. There's some feedback that you can give there. And also eligible for PHI credit. I believe that all you need for that is going to be the ID number and the course name. So do you filter your water? Greater than half of all Americans filter their drinking water at home. So this is something that we do think about, and sometimes we don't think about it until things go wrong. If the water supply is tainted or there's lead in the water, then all of a sudden it becomes a crisis. But the water we drink is so important to our health, and the same thing with the air that we breathe. So this is the ERV and HRV systems are very not new in Europe. Again, Brink is a company that's been around for 40 plus years, but they are relatively new to the US. And a lot of that has to do with our buildings becoming more and more high performance, more airtight, which is mandating kind of that we have these systems. So what about the air you breathe? Again, that is very important to our health. We spend 90% of our time indoors, and we can think about fence-line communities where communities near highways, which have much higher rates of asthma, where we really see the impact of our air on our health. So we want to make sure that that air is quality. Indoor air is not only better overall well-being, but better sleep. When we sleep, doctors talk about how important sleep is on our health. And one of the reasons for that is that's when we rest and digest and have all our cellular repair happening in our body. And in order to have excellent cellular repair, we need oxygen for that. oxygen, is going to be our friend with, we want a direct supply of air to the bedrooms. We see, oxygen bars if you're at altitude or have a hangover. We know that how important oxygen is, that can really, really help with that repair from whatever we've done to our bodies. As we spend 90% of our time indoors, why do we want air there? It's not for the building itself, it's because humans need to breathe, and we want excellent indoor air quality. So we want a fresh supply, and we want to dilute the air that's there and pull out these toxins. What are some toxins that are in our homes? That could be nitrous dioxide, which comes from cooking. This has been in the news a lot lately. I think I left out that formaldehyde. So again, we want to pull that out and dilute the air in our homes. Carbon monoxide, we have carbon monoxide detectors in our homes, so we know how important that is to our health. But that's when, you're getting close to lethal levels. At much smaller quantities, you're going to still have harmful effects such as headaches, etc., and other issues. CO2. Poor mental performance has been associated with high levels of CO2 and is something that we measure, which is often an indicator of the levels of other toxins. Ozone also, high levels of ozone have harmful effects on our health. Radon and cleaning compounds. So we're spraying, various cleaning compounds, bleaches, any chlorinated or fluorinated compounds. We want to remove those. So when we're cleaning, we're, releasing these compounds into our homes. VOCs, which is coming from furniture and paints, we want to remove those as well. And water. We need water to live, but too high and too low concentrations of relative humidity has a great effect on our well-being. So we can go to the next slide here. The Goldilocks zone is we don't want to have too low relative humidity or too high relative humidity in our home. As too low relative humidity, we start seeing higher levels of asthma and other respiratory issues, and too high relative humidity leads to other issues, bacteria and mold growing in our homes. And then the graph on this control indoor air humidity, we see moisture accumulating in the home on the right-hand photos, as well as these photos close up of our mucous membrane. So we can see why the relative humidity has this effect on our health. With low relative humidity, you start our mucous membranes dry out, and we have these kind of highways for pathogens into our body. Next, we have a study here showing just the direct impact of indoor air quality on students as well as the workplace. So there's a direct correlation between the CO2 levels, and we spend so much money on our workers, training them, everything, but we want them to work, have the ability to work, and CO2 absolutely affects that. Actually, we have a CO2 monitor increasing our ERV and HRV in our office, and if it gets turned off for a holiday and forgot to be turned on, I can immediately tell that, and know that something's up. And sure enough, I can detect just based on feel that the ERV is off. Next, comfort. So we want to control how the air gets into our homes for comfort reasons. So if we have uncontrolled air coming into our homes, we feel draft. This is just a little story inside of a restaurant that I went to at Bear Mountain, New York, and it was a beautiful day, beautiful views, but pretty cold out. And the hostess was only seating everyone around the fireplace because the windows were so drafty. So kind of you have this, all this real estate that was underutilized because of the draft. So next slide, what can we do to get proper ventilation? Sometimes we think we can just open a window. I love windows, big fan of them. But if it's cold out, you don't want to have to open your window every 15 minutes to make sure that you're getting proper ventilation in your home. And then again, drafts and the quality of that air. So, I know this trick is something that my mom does, kind of like a little saran wrap filmed if there's drafts there, because we can, really feel uncomfortable when we have drafts. So we want to properly seal our windows. On the right is a great install detail of just how we're making sure there's no thermal bridges and no drafts around our windows. So passive ventilation is the next slide. So at the Passive House Network conference in Denver just last year, I believe, Jonathan Hines is a great speaker. He's from the UK, from a company called Airtight, and they really studied and researched passive ventilation and how you can just bring air naturally, work with the natural flow of air, heat rising to get ventilation through schools. And next slide, built these beautiful schools. However, he was horrified when, years later, they ended up studying the CO2 levels, and especially in the wintertime here and much of the fall was above these unhealthy limits in schools. So that was a big proponent of mechanical ventilation. So next slide. So how do we do it? So we built high performance buildings. Of course, we know Passive House is a great method to this because we know that it's performance based, but we want to have continuous insulation, no thermal bridges, great windows, air tightness, and to couple with that, we need the fresh air mechanical heat recovery system. All right, so next we can look at the order of importance. So we obviously need to shed our water from our buildings, otherwise we wouldn't survive and our buildings wouldn't stand. But air control is the next, what we see as the next most important there. So you can click on the slide here and we can see that it delivers health, energy and health. So then we can think about vapor control and thermal control. But again, we'll focus on air control here. Okay. You can go to the next slide here. This is an NREL study talking about how the direct correlation air control has on our energy use. So infiltration is a huge, energy suck because we have to, heat all of our air, cool our air that's coming in from the outdoor if we don't use mechanical ventilation. So next slide is types of systems. So we do require in code mechanical ventilation. So exhaust-only systems are commonly used. Code has continuous ventilation requirements, or you can do it through exhaust-only systems. So that's going to be your bathroom exhaust fan or kitchen exhaust fan. And so you have these multiple penetrations for each bathroom or, your kitchen hood, pulling that air out. However, then that air, the same volume of air that comes out needs to come in somehow. And so where is that coming from? So you can click on the slide here and we can see, you're creating this negative pressure in your home, and the air is going to want to come in any way that it can, through any cracks, it's going to come in through maybe our attic, maybe our crawl space, in a very uncontrolled way. So not only is that going to come in at the same temperatures outdoor, but dust, bugs, things like that. And conversely, ERV system is going to be a balanced ventilation system. So we put in exactly the amount of air in as air out, which means that our homes are going to be at neutral pressure, not incentivizing any pull of air through these crawl spaces, cracks, dusty areas. And you can control the route that is getting in there. Controlling the route then allows you to pull the air from the freshest source possible. So we want to make sure our supply is on the freshest, where we're getting the freshest air possible. We want to make sure that air is quality. We can filter the air because we know where that air is traveling. comfort, we can use heat recovery and energy recovery to make sure that that air doesn't feel drafty. Intentional delivery, that air is not going, to wherever there's path of least resistance. We're directly injecting the air into the bedrooms where it's needed and pulling the air from these contamination sources. And you have energy savings while doing so. So in terms of balanced ventilation, next slide, there's decentralized and centralized systems. As you saw, we supply both here at 475. The decentralized systems are through-wall systems and work in pairs. Decentralized systems just have the one intake, one exhaust, and then use ducting to distribute that air throughout the home to all the spaces. Next slide. So quick on just the decentralized systems. They're great for maybe retrofits and also larger multifamily buildings where you can have individual systems for each unit. So this is a multifamily and a retrofit project here. Next slide. So as you can see with the centralized systems, they have insulated ducting coming into them, and then this is a home run system. That's what we supply here at 475 that uses 3-inch ducting. And I'll talk more about that later, but comfort criteria. So for passive house, we do have a comfort criteria which mandates a certain supply air temperature so that we don't feel draft. How do we get to that comfort criteria for supply air temperature? We have to have a system with high efficiency. So in order to get the mandatory required 63 degrees Fahrenheit supply air temperature when it is 15 degrees Fahrenheit outside, we have to have a system that is at least 84% efficient. And then we can see homes where the windows are all sealed up, such as this beautiful passive house on the next slide here, where the kids are just reading in the windows. You can see how comfortable they are because the air is not coming in through those around the windows. It's coming in through the ventilation system. So the next slide is showing the power of the Passive House Institute certificate. ERV and HRV systems are sometimes the manufacturer will declare the efficiency of the system, but having the PHI certificate on an ERV and HRV systems means that it's been tested by a third party and they have specific methodology on how they get that efficiency. Sometimes you can see, manufacturers aren't lying on their efficiency value, but the efficiency can be taken in many different ways, such as if you're looking at the supply air temperature. When it's cold outside, you could be factoring in a very inefficient motor that creates heat. And then therefore, if that heat from the motor is factored in, you're going to get, pretty warm air. The Passive House Institute looks at that and they look at the outgoing air temperatures to get the efficiency value. So you know that across the board, it's the same testing methodology. They also look at how quiet the unit is, minimal case leakage, other values here. So it's something great to look for. And they also have a penalty because just that they found in a study that the manufacturer rated values were much lower than were much higher than what they found in their study. The next slide just shows the Passive House certificate. The 12% came from, I think, what they found is the disparity from the what the manufacturers, an average of what the manufacturers said versus what the PHI found to be the efficiency of the systems. All right, the next slide after this talks about filtration. So that's another great benefit of having a dedicated mechanical heat recovery ventilation system. So we saw, Canadian smoke for me in New York, that came down and really affected the city. California has, smoke and is a concern here as well. So we want to, in those cases, filter the air. So next slide, we can see, we know where the air is coming from, and we can add these filters. I would recommend at least a MERV 13 for the supply. That's what the Brink system has, but we, you can see the types of things that are filtered with a MERV 13 filter. We have lead dust. If any kids have allergies, pollen, dust mites, mold spores, these things. So filtering that air supply is a great way to create indoor air quality. The next slide, so we can see after that wildfire smoke in June 2023 from Canada coming down, how our office filter looked. So it was pretty nasty, but we were very happy that we were filtering that and preventing that from getting into the office. All right, next slide, ERV or HRV. So a little bit about the differences here. The HRV only recovers the sensible heat. And so it uses a vapor closed material, airtight and vapor closed, but it's conductive material so that the heat transfers from the exhaust air to the supply air, so that whatever temperature, it works in the summertime and in the winter, whatever temperature you're heating your home to, that the system works to maintain that. An energy recovery ventilator uses a material in the core, the ERV core, that is airtight, because again, we don't want that air coming from our bathrooms to going into the supply air, but it's vapor open, so we can start recovering some of the moisture. When do we want to do that? So the next slide talks about when do I use an ERV or HRV. So you would want to use an ERV if you have either very humid, hot and humid summers, or very dry winters. And that's because in the summertime, we can reject much of that summer humid air, which leads to more comfortable interior conditions, especially for air conditioning. That means your interior relative humidity is going to be lower. And then in the winter, we want to hold on to some of that moisture and not bring in too dry of air and then heat it, leading it to the relative humidity to be even drier. So in many areas of California, actually, if the relative humidity is ideal, then we can use an HRV, which has even higher sensible heat recovery, and it can be a great system. But ERVs are definitely recommended if outdoor humidity, high or low, is a concern for you. It also depends on interior conditions of the home. Of course, if we have high interior humidity loads, then, we want to relook at it. And that's why sometimes HRVs can be a good solution for multifamily buildings. So how the core works, so you have the air streams passing by each other. You can think of straws. So, put your hands together, fingers interlaced, and we can think of the air moving in one series of straws and passing by the other. And we can, the heat is transferred, but the air is not. So that's the cross-counterflow heat exchanger was one of the earlier stationary plate heat exchangers. And then the cross-counterflow heat exchanger made the system that much more efficient by this hexagonal shape, which increased the surface area for those two air streams to hang out longer. So the surface area and the amount of time that the heat has to move from the two air streams increases the efficiency that much more. All right, so what is the latest technology here? So vane anemometers are a great addition to the HRVs and ERVs. So that's going to be put on the supply and the exhaust fan. And not only is the heat recovery core, how large and how much surface area you have, going to maximize your efficiency, but if we can make sure that the supply and exhaust air streams are perfectly balanced, and not, one having much more flow than the other, then you're going to dramatically increase your efficiency as well. So having this, very fine, precise measurements to make sure that those are in balance allows us to get high efficiencies without using the most massive core that you because size is also something we need to factor in when we are installing systems and building homes. Distribution systems matter. We supply a home run system. You may or may not be familiar with it, but essentially it takes all that supply air and converts it into 3-inch ductwork, which fits into a 2x4 wall. And you can, we will bring on 1, 2, or 3 of these to the different spaces to get different levels of supply and different exhaust extract values there as well. So you're going to have a supply and exhaust manifold. Using a company that has a complete kitted system reduces the risk of errors and keeps everything airtight as well. So on the intake as well as the exhaust, so your ducts connecting to your exterior, you want those to be insulated. So this is a great insulated duct solution that's nice and airtight, because not only in the wintertime is that air going to be very cold coming in, but because we have such a high efficient core, the air leaving is also going to be almost as cold as the outside air. So both of those need to be insulated. And then we have our semi-rigid duct that is not insulated, so that should be within the conditioned space. And if it does need to exit the conditioned space, we need to think about insulating that, possibly building a box around it, something like that. So we can see here other components of the home run system include diffuser boxes, which convert multiple of those 3-inch ducts to one diffuser so that you can get more supply or more extract rates there. On the left, we can see a new build, and on the right, we can, the middle picture here, we can see a retrofit. And then we have our diffusers. So these can be even as pretty as a design diffuser and be painted as well. So high wall or ceiling mounted is a great place for those diffusers, and placed in a way that it promotes cross ventilation throughout the home. Optional accessories. So you can, with these ERV and HRV systems, have a relative humidity sensor, CO2 sensors. The relative humidity sensor allows you to have automatic boosting of the system when increases in relative humidity from the return airstream is sensed. And that allows, the nice thing about these is it's not like a bathroom fan where if you don't turn it on, you have nothing, you have no exhaust. There's always continuous exhaust from the bathrooms pulling that relative humidity continuously, but we can also boost the system. So the system is sized for normal operation, and then we can pull relative humidity as needed. CO2, not typically needed for a normal home, but as I mentioned, we have one here in the office because the levels of occupancy change throughout the day. So if you do have a space like that, some sort of office, it can automatically ramp up as necessary to keep the CO2 levels within range. And then on the right, we see a boost switch, just a manual way of boosting the system to the higher flow rate for 30 minutes. We have a touch control. You can change everything from the touch screen on the unit itself, but if you want control at another location, that's a great add-on. And then we see a plus module, which allows you to connect to the Internet of Things and BAS systems and use, apps, things like that, as well as systems like this, which is for our system with a Brink Home. You can start trending data here on this next slide. So we can see all the values that we can trend. It trends even more than this, but it's not quite super cold, but you get an even more dramatic graph when it gets very, very cold, where you can see that the outdoor air temperature coming in is much colder than after it's gone through the core. So you can look at things like that. You can look at the pressure of the system in the CO2 sensors. Some of those things you can trend. All right, the next slide, we talk about what you need to know. So as an architect, what's important when thinking about ERV and HRV systems. So this is a quote from Barry Price, who's an East Coast architect, been doing this for years. And he said he's been in the difficult position he's constantly defending the mechanical room. He's sometimes failed to do that early on, and he's lived to regret that. So what does that mean? You know, if homeowners are looking to get every inch of livable space, sometimes the mechanical room is cut short and made smaller, but you want to make sure that you can still run your ducts smoothly, and that will lead to a higher functioning system if you can have a good ducting system. So it's a recipe, and it's not only about the ingredients, but it's how you put it all together. So you want to coordinate, in design development, you want to coordinate the equipment, access to the outdoor air, duct runs, diffuser locations, and be proactive. So here we talk about, okay, how much room do I need to defend in the mechanical space? So if you use kind of a compact unit, less room you need to defend. The next slide shows a nice design here where the unit was placed on an exterior wall, minimizing the runs of those insulated ducts. And that is important because, again, that's bringing in either very cold air in the winter or hot air in the summertime. So making those nice and short is great. Brink does mandate that there's a 5-foot separation between the supply and exhaust, and many codes actually require a 10-foot separation because they don't distinguish really between ventilation exhaust and more noxious exhaust. So long duct runs can reduce the efficiency. This is a nice example of a system where you can see it's very close to the wall, so those insulated duct runs are short. However, they chose to move the manifold to somewhere more central in the home. The benefit of this is, again, you have those short insulated duct runs, not a lot of heat loss going to your cold air stream, but you want to keep your 3-inch duct runs, the average of them, shorter as short as possible to reduce the pressure losses there. So you can use these nice larger snap lock duct to place those manifolds in a more centralized location. And we want to try to make those duct runs pretty equidistant if possible. If you can't, this might mean if you have a really short run, the air is going to want to travel there. You might even want to do a long loop to make that at minimum 10 feet, the short runs from the unit. Also, we want to think about maintenance. So you can put your supply and exhaust on the roof as well. We have these roof kits, termination kits, but we do want to place them in a place where you can see them and check on them. So cleaning the supply is an important step to make sure that you have a great system. Where you place that is, again, also going to make sure that you keep that clean. I've even heard of, not placing it under a big floodlight that might attract bugs to the system. Of course, we want to avoid, condensing units that could affect the temperature of that air supply, barbecue grills that could, affect that air supply as well. And also the kitchen filters, we want to, the kitchen diffusers, the kitchen exhaust will have its own filter. We want to change that as well. And here we talk about commissioning. So with the Brink unit, we know that it has the vane anemometers, keeping that supply and exhaust balanced. However, because we have different lengths of duct runs, the air is going to want to travel through the shorter ones. We do factor that in when designing system. However, the diffusers themselves you can change the aperture of those diffusers to restrict or increase the airflow there. This design diffuser has a 9-step flow balancing valve, and the metal one has a screw there that you can tighten or loosen to increase or decrease the flow. And then we want to measure that to make sure that we are getting the flows that we want in each room. So in summary, we want a distributed, balanced, continuous system with energy or heat recovery. Ventilation certifications help to make sure that we can trust all those values and that those values are being looked at. Filtered, proper indoor air quality, quiet system that reduces the risk of condensation, mold, and toxins in your building. So thank you very much. 475 is here to help. We can design a system for homes, create a distribution plan, do a takeoff and quote, and we have great, these systems are supplied here in the US, and we have great backing by Brink in the Netherlands. I've been to their factory, excellent R&D team, excellent quality control team. So great support there. All right, so 15 minutes here for questions.
You must be muted, Kim.
I am muted. Here we go. Thank you so much for that presentation and for sharing that with us today, Gabrielle. Seeing a couple questions in the chat. I think you got to one or two of them as we went through. Christian, do you want to unmute and ask all of your questions?
Yes, I'm happy to do it. Yeah, question would be, first one, are these equipments from Brink UL listed for the US market here? Always a big topic. And then the second one, maybe you can elaborate a little bit on the main common parts between the Zehnder Comfort units and the main differences, maybe.
Sure, absolutely. I would be happy to do that. So yes, they are UL listed. We have received UL on the 325 units. That's going to be 191 max CFM, and the 400 units, about 235 max CFM. And we are working to bring in additional sizes as well, which means smaller and larger units. And those are undergoing UL certification right now. So. In terms of differences between the Zehnder and the Brink system, great question. They are definitely the robust, high performance, highly efficient systems used throughout Europe. So most homes in Europe use one or the other. They actually are both manufactured in the Netherlands. I've been to the Brink factory and then went by the Zehnder factory. They're very close to each other. Brink is actually #1 in sales for the Netherlands itself. Kind of differs from country to country, but both kind of like the big robust systems. Some of the differences include the insulated ducting I really like with our system. The touchscreen, I've heard that's much more intuitive touchscreen control there. The huge difference is going to be that vane anemometer. So the Brink system is the only one that uses that to balance supply and exhaust. So I have heard, some few systems in places of altitude kind of being affected by atmospheric pressures. So the Brink system is going to work to supply and exhaust those flows no matter what, if there's any system pressures. So that is definitely a big factor there. I can send a whole list of them. Please feel free to email me.
All right, we have a couple questions from Alan. What do you suggest the ACH value that is worthwhile before having an ERV, HRV installed?
Yeah, absolutely. This is something that we look at for every single project. And so we look at ASHRAE levels, ASHRAE recommended levels for ACH. So that's going to be, for normal operation, we, keep that in the range of like 0.35, and then on boost mode, that can increase. But we definitely want to make sure that there's adequate movement of air throughout the home at all times. But we also want to make sure that you're not bringing in too much air. We don't want to have any wind tunnels. It could also dry out the space more than we want as well. So, or bring in too much humidity, because as we know, the ERVs have humidity recovery, but in places with high levels of humidity, it is bringing in some humidity because we're increasing the amount of fresh air coming in.
Great, thank you. And then another one from Alan. How popular are the HRV ERVs in the market of California compared to somewhere in the East Coast like New York?
Great question as well. So we are actually seeing a lot of interest in the ERVs and HRVs in California in particular. I think that it's actually the third busiest state for us in the US. Canada is keeping us busy as well, but it's up top there.
Great. Yeah. I'll invite anyone else who has a question. Feel free to either put it in the chat, or you're also welcome to unmute and ask a question.
I had oftentimes seen that they recommend air intake and exhaust up at the higher part of the room. Is there any particular reason for that, or could you put them one at the low and one high, or both low, or anything like that?
Yeah, so I generally recommend them to be both in the ceiling or high wall. A exhaust especially is great to be in the ceiling. But for the supply, within kind of where the occupant's height is, is a great place for those supply diffusers. So we do see that you want to make sure that these are placed where they won't be blocked by furniture, things like that as well. So that's also a factor when placing these, but generally high wall and ceiling is where we recommend those. The design diffusers actually have a great Kawanda effect because the air comes out the side of the diffusers, which means that the air kind of hangs onto the ceiling and can travel further into the room.
Is the reason only because of the blockage by furniture, or is there any other reason?
Also within kind of the occupant's height, so kind of supplying that air where occupants like head level, I believe is also one of the reasons why we recommend high wall there.
Okay, thanks very much.
But I have seen some systems do the low to high. Yeah.
Another question from Alan. Can you explain more about the enthalpy?
Sure. Yeah. So as mentioned, the ERV recovers the moisture that's in the latent phase so it recovers relative humidity, not just sensible heat, but also latent heat. So enthalpy, ERVs do that, recover the enthalpy of the system. And that means that it takes a lot more energy to, as we know, to go to a gaseous state from liquid to gas. So that means that the sensible heat is going to be reduced for ERVs slightly. So a lot of times if you can use an HRV in your climate, it is recommended to do so, but you will be spending a lot less energy on dehumidification or humidification, which takes a lot of energy if you use an ERV for an appropriate climate.
Great, thank you. Any other questions?
Alan had a couple of early questions. So one was there was 12% was on one of the slides, and he asked where is that 12% from? And then at 1237, he asked what is the R value of the hose? So we'd have to look at the slide to know what those questions are. But if you're comfortable with that, Gabrielle, and you could go back and take a look at where the 12% came from and the R value of the hose.
Yes, I do recall when those were asked. So the 12% was that Passive House standard, which calls for a penalty if you don't use a Passive House certified ERV or HRV system. And that's because that was a Fraunhofer Institute study studied that, okay, this is the manufacturer declared values, this is the PHI declared value. There was a disparity, and the average was, I believe, around 12%, and therefore you can use a non-Passive House certified system, but you need to take that penalty, and many times that causes you not to be able to use maybe a certain ERV or HRV on a Passive House certified system. And the R value, I'm not sure of it exactly off the top of my head, but we do have it on the website. We have all the cut sheets and all the spec sheets for that insulated duct. Again, very airtight, very easy to install. It has these rubber gaskets that snap into the next one so that you can easily add a 90 degree. You can cut those in half, or a 40 degree to make a nice, well-designed system. They are, for most climates, adequate as long as you don't have excessively long insulated duct runs. for excessively long duct runs, or if you're in a very cold climate like we see in some regions of Canada, you may want to over insulate those ducts as well, because it is bringing in that very, very cold air.
Great, thank you so
Most
much.
projects, it is, yeah. Yep.
Wonderful. Any other last questions? All right, then Jay, would you like to send us off with a call to action?
Yes. Give me here. I'll just do the share. And it is the call to action is what I'm sharing. I might mention there was a call to action, or Alan Chen put there was something else. It wasn't a question in the chat, but it was a request that I think is a good idea. And it's something that we've normally done, but apparently didn't happen with this one. And that is, just a few hours before the actual community meeting or webinar, if you send out an email to all of the people who have registered, then they'd have that be reminded of the link to get in. So that's a good idea, and it's something that we normally do, Alan. I'm also looking in the chat. They're not questions, but I did put the links in the chat to two, and we're looking at the call to action now. I believe. The call to action, beyond the call to action, we have a virtual community meeting coming up on the 19th of November. That's next Tuesday. And it's eliminating makeup air smart mechanical solutions for small passive homes. So if you wanted to attend that, the link you can find the link on the website, or the link is here as well. And then oops, not that, a different button. Oops. And then on December 3rd, we have another webinar, coming up, the right size plumbing in homes and apartment buildings. That's presented by Southern California Edison. And again, the link to that is in the chat. That is there. So if you want to attend further meetings, I think that would be, that's an easy way to get to it. And in terms of supporting Passive House, because we try to do these things in Passive House, and there was, by the way, just literally in the last on the 8th in Wall Street Journal, and I'll put this up in. I'm not sure you all be able to see it, but the Wall Street Journal has an article called "New Tech Tries to Catastrophe-Proof Your Home." And it's not just about the basics or the basic things of Passive House, but the idea that a Passive House is much more resilient to hurricanes, floods. You can build homes to that capacity. So it's nice to get that coming from the Wall Street Journal. In terms of Passive House California, down at the bottom, you see we have passivehousecal.org is where you would find, if you wanted to sign up for the newsletter, it's under the news section. If you wanted to become an individual professional member of Passive House, it's there. If you want an organization or your company to become a member or a sponsor, or if you want to donor or volunteer, that information is there and available. So we'd love to have you. And again, thank you very, very much, Gabrielle and 475. That was just excellent, I believe. And those of you who've been here are like the light bulb that's lit here, and that you've learned some things that you can share with others. And in this little picture, the only light that's actually lit is the one in the center, but it's carrying over to others. So thank you for your time and attention. And info at passivehousecal.org is where you can get to board members and other things to find things like that. So thank you all very much. I will stop share, and we can we have a whole another almost minute. So anything else? Any further questions? Anybody want to bring anything up?
Thank you again for having me. Yeah, would love to hear from you all. Feel free to jump on the website, fill out a jot form request, and I would love to hear feedback on the presentation as well with that QR code.